Hi, and welcome to this second video that I'm presenting to you about the topic of shifting equilibrium. So if you haven't seen the first video on this topic, please link back to this video after you've seen the first video. I will try and put a link in the comments and in the final window as well, so you'll be able to catch up with everything that you need to. So with the last video, just to give you a little bit of a reminder, we actually talked about changing conditions and seeing how that would actually affect the equilibrium of a reversible reaction within dynamic equilibrium. And the idea that helped us summarize everything was that when a reversible reaction is in equilibrium and you make a change, the system acts to oppose that change and restore equilibrium. It's a very fast way of getting to the right answer, but then what you need to do is you do need to make sure that you start talking about how maybe one of the reactions, maybe the forward reaction is, for example, is happening at a higher rate than the reverse reaction, and how that then drives and shifts the equilibrium over to a particular side. So please watch that video that I did earlier. We ended with a quick summary of all of the ways in which I can imagine they could ask you about, they could ask you to talk about this topic. So where we left off was we started talking about, would a temperature rise actually help a reaction if we wanted to drive a reaction forward, for example. And if the forward reaction is, for example, exothermic, then that means to say that the backward reaction is favored because the backward reaction is endothermic. So as a result, you will have backward reaction rates happening higher than the forward reaction rate. So the forward reaction rate would be lower than the backward reaction rate. The equilibrium will then thus shift over to the left until the rates even themselves out. Less products would be made, which is not very good if you're running this through industry, and more reactants would be made, which is not helpful because that's what you start off with when you have these industries. If you, however, have a forward reaction that is endothermic, the forward reaction is favored if you raise the temperature. The equilibrium shifts over to the right, and you get less of your reactants that you start off with and more of the products. Now, what I need to do is I need to make sure that you are also able to appreciate the idea that temperature just generally helps everything along. So there's nothing really there's nothing really new. I mean, like when you study GCSE chemistry, you always get told temperature is always something that helps a chemical reaction. And the reason why that happens is because temperature is actually needed to supply energy into your chemicals to start breaking bonds, which is usually what happens when you initiate a chemical reaction. So what you need to understand is that with dynamic equilibrium, you actually have a forwards reaction and you have a reverse reaction. If you're breaking bonds for the forwards reaction, you also are getting energy to break bonds in the reverse reaction as well. So both the forward and the back reaction rates are increased when you are raising the temperature. But if the forward reaction is exothermic, it's the reverse reaction that is endothermic, and the endothermic direction is actually something that gains the most advantage from a rise in temperature from the surroundings, because you're supplying energy to the reaction for it to then proceed at a higher rate. So although all particles speed up for both reactions, increasing the number of successful collisions taking place per unit time, raising the temperature indefinitely will help endothermic reactions if the endothermic reaction is going forward. However, if you have an exothermic change going forward, then what you need to do is you need to raise the temperature, but not too high. The other thing that we started talking about was what would happen if we actually change concentrations. And generally speaking, if you raise the concentration of any reactant, that actually helps because it shifts the equilibrium over to the right. You get more products and you get less reactants because the forward reaction is taking place at a higher rate. That means to say that your reactants will start to deplete, and then your equilibrium shifts over to the right hand side as you start to get the products turning back to reactants. But if you keep raising the concentration of the reactants, that will actually help drive the equilibrium forward to the right hand side. and over to the right hand side, I should say. If you are doing this as an industrial process, or if you have a chemical reaction, if you have a situation where the product concentration is going up and up and up, the equilibrium actually shifts over to the left hand side. You get more reactants and less products as a result. So you can use these two now. Pressure and catalyst is something that we're now going to be focusing on, and we'll be using an example, which is the Haber process. And the Haber process actually was considered around about uh, less than 5 years after a massive explosion occurred, which nearly killed the assistant of Le Chatelier. So Le Chatelier was almost on the brink of superstardom when it came to chemistry. And what happened was the reason why was because he actually had some air that was left and trapped in the apparatus, as the accounts suggest. So he almost figured it out. And in his words, near to the end of his life, he actually said, "I let the discovery of the ammonia synthesis slip through my hands. It was the greatest blunder of my scientific career." Now, hopefully, we won't be making any blunders today in the video. The video that I'm going to start taking you through is actually linked through the QR code. And it starts off with talking about what the most important discovery is, and arguably the most important discovery is the Haber process, because it leads into so much of what we have in our everyday life. So the Haber process is essentially, and I'm just going to do a little commentary on this as and when it's necessary. Please remember, by the way, that these subscripts must go below the line. So the top of this tune must be below the line. I think it's just to enhance the quality of the presentation. But please make sure that that is correct. So the Haber process, and I've got a correct version, by the way, on the next slide. If I just show you here, this is a more correct version. So here we go. All right, so please make sure that your subscripts are below the line. But the Haber process is an equation where you just have nitrogen reacting with 3 hydrogens, and that forms 2 molecules of ammonia. If I just get back to this part, so over here we go. So the Haber process consists of this single nitrogen molecule. And what you have to do is you have to snap that apart. So you introduce the nitrogen as part of this process. You have 3 molecules of hydrogen, for every molecule of nitrogen. So you have to snap these apart and then you recombine them. So each of the nitrogens is then surrounded by 3 hydrogen atoms. Okay, and that makes up your ammonia molecule. Now, the big issue is that nitrogen is actually really important for agricultural purposes to actually form fertilizer. And the problem is that there's so much nitrogen. It's around 78% of the air that you are breathing in right now that consists of nitrogen. Now, we don't have 7 billion people now on this planet. We actually have 8 billion people. So it's really important for us to be able to ensure that plants that eventually get harvested get the largest yields, and we use fertilizer. We can't rely on natural fertilizers to provide the level of food that the world actually needs. The plants actually take it in through the soil, through their roots, and it takes it in the form of soluble nitrates, I should say. Plants cannot absorb the nitrogen from the air. There are certain bacteria that can actually do that naturally. They can provide sources of nitrogen, but to utilize the massive resources of nitrogen that we have in the air, we rely on this process. This process was pioneered by Fritz Haber. He actually managed to get it done properly before the Chatelier did. So we're looking at some examples of foods that it can actually help make. So we start off with chemical equilibrium in order to build our understanding. When you have a reaction in a closed system, in a closed container, if you start off with hydrogen and nitrogen in a closed container, if you allow them to react in under certain conditions where you have the temperature high enough for the reaction to start, you actually start finding that your nitrogen and hydrogen start to diminish and your ammonia concentration increases. But the problem is that the reaction starts to slow down, and the reason why the forward reaction starts to slow down is because once you get to a certain point, the ammonia starts to break down. It is continuous to break down, but the rate of reaction for your breakdown of ammonia actually uh, starts to affect how much ammonia you can actually get. So what happens is you find that your nitrogen and hydrogen levels go down, but then the rate of decrease becomes lower and lower and lower, and your actual ammonia goes up and up and up, but the rate of increase of ammonia actually decreases as well. If you have a system in equilibrium, like nitrogen and 3 hydrogens giving you 2 ammonia molecules, if you increase the amount of pressure in the system, you find that your yield of ammonia actually goes up and up. Now, the analogy that the video uses is a crowded room, but I'll talk to you a little more about that because I think it does go a little beyond what can be picked up from this principle that the Chatelier came up with. So it's not just the case that it wants to form ammonia. There's a little more than that. But Haber realized that large amounts of ammonia can be made if you actually use if you actually compress the nitrogen and hydrogen. You pump it under pressure, and you use catalysts, Moron catalysts, in a short while. So all we need to do is just whip forward now. So here is your hard processor. You do actually need to be able to state this equation. You do also need to be able to give the reversible sign. Now let's think about changing temperature. How will change that? Will changing temperature help us obtain more ammonia? Now the issue is that the forwards reaction, the desired reaction, is actually exothermic. So if you have an exothermic reaction overall, supplying a source of energy to through warming the chemicals doesn't actually help, because although you do need a little bit of energy supplied to start breaking the bond, so a temperature would help, a rise in temperature would help. The problem is that the forward reaction, if it's exothermic, is not endothermic. It's the reverse reaction that becomes endothermic. So if you are actually supplying extra energy, the reverse reaction is actually encouraged. So heating speeds up both reactions, but the endothermic reaction is the one that's favored. The backwards reaction, where you actually have ammonia breaking down and back into a nitrogen and 3 hydrogen molecules, is actually favored. So if you heat it up, you're going to get more of this process happening and not so much of the forward process, the forward reaction of nitrogen reacting with hydrogen going to form ammonia. So it's not very good, because you actually have, if you can imagine, you've made your actual product, which is ammonia, and now you're starting to break it down. That just doesn't make sense. This little seesaw over here, you can utilize and imagine that if we had a complete reaction with no backwards reaction, you would get 100% product. So where this triangle is actually showing the position of the equilibrium. But so if you are actually heating it up indefinitely to higher and higher temperatures, what actually happens is you lose your product and you start reforming your reactant. So you're much worse off than before. So to conclude with the issue of temperature, does raising temperature help us to obtain more ammonia? Initially, yes, but then what happens is you get to a point where it becomes counterproductive. In the initial part, you actually help speed up both reactions, both the forwards and the backwards reactions. So it's not a very, very good thing. So what you'll need to do is you'll need to find yourself a bit like, a compromised temperature, like like Goldilocks's porridge, not too hot and not too cold. Okay, so we've dealt with temperature. You need it to be warm enough to start breaking the bonds, but you don't need it to be too high, such that you start encouraging the endothermic step, the reverse reaction. And now we're going to look at what happens with pressure. Now, let's just think about this concept of pressure, because a lot of people get confused about this concept of pressure as going into the GCSEs. But when we're talking about pressure, pressure is actually the interaction of a molecule on the inside of a chamber wall. So here's our closed system, our closed container that we're saying, right, this is part of the industrial process. Everything is happening. All of the reaction is actually happening in this chamber here. Now, what you've got to try and understand is that these under the conditions of temperature and constant pressure, what you will actually find is the reaction takes place. Yeah, and you'll set up your equilibrium, which is fine. If you actually start injecting more molecules, more of your nitrogen and more of your hydrogen into this chamber, what actually happens is you get more molecules bashing on the inside of the walls. That means that your pressure is increasing. Now, so what you could do is you could try and squeeze more molecules of your reactants in until you get to a stage where the higher pressure that you have with the gases coming in is equal to the pressure that you now have established within your box. So let's say, for the sake of argument, you have more molecules squeezed into this box, and that is like your higher pressure situation. I want you to imagine that this over here is like an imaginary gate. Okay, so if the pressure inside this box is the same as the pressure of the gases that are trying to come in, there's no net flow. It's not going out. It's not coming back in. Why does that actually help? Well, if you think about it, when you actually have this forwards reaction, you have 4 gas volumes on the left-hand side. You have 3 molecules of hydrogen and 1 molecule of nitrogen reacting for every 2 molecules that could potentially be made of the ammonia. So 4 gas volumes on the left-hand side become 2 on the right-hand side if you have a successful reaction between these 4 molecules. If you're finding that that's happening and you're making your target molecule, which is the ammonia, what then happens? Well, what then happens is that the pressure actually drops inside the chamber, because you had 4 molecules, you now have 2 molecules bashing the inside. And according to Avogadro's law, it doesn't really matter whether the molecule is ammonia, nitrogen, or hydrogen. If it's hitting the inside of the chamber, it's going to have a little force on it, and it's all going to add up. So whatever the gas molecule is, if you have less gas molecules, your pressure is going to go down. So that drop in pressure, you can imagine, allows more nitrogen and hydrogen to enter the closed system. And that means to say that it's actually drawing in the reactants to form the products. It's actually a really, really useful way of thinking about it, I think. So as a result of raising the pressure, you actually find that you are able to make more ammonia. The higher the pressure, the more ammonia you should be able to find you make. The amount of ammonia in the mixture increases, and equilibrium is shifted over to the right, because you're actually allowing the nitrogen and hydrogen to form the ammonia. So that's a really, really good thing. We're on the right track if we were in charge of an industry like that. So this drop in pressure allows more nitrogen and hydrogen to enter the closed system and continue. And what we actually find in reality is that we also incorporate a way in which to try and condense this ammonia down. So we condense it and remove it completely from this closed system, and we compress it and we cool it down and we take it away and we just remove it in tanks in the industry. And so what you're doing is you're actually removing all of this product. And again, if you lower the amount of products, if you have a way of lowering the amount of product, the shift in equilibrium goes over to the right-hand side, because your forward reactions are forward reaction rate is higher than your reverse reaction rate. Obviously, if you're removing the ammonia, you don't have that many reverse reactions taking place. So that's basically the explanation behind that. So we can reduce the concentration of ammonia by allowing it to go into what's effectively a very large fridge. If we have the gases that come out from the reactor going into this cool chamber, the ammonia actually liquefies first. There is there is a big difference between the boiling points of hydrogen and nitrogen together with ammonia. The ammonia actually cools down to form a liquid first because it actually has a higher boiling point. So if it has a higher boiling point, it will liquefy first. The ones with the lower boiling point will actually take a lower temperature to turn it back into a liquid. So you just allow all of it to go through the ammonia, and you cool it down. You then hit the boiling point of ammonia first. The ammonia forms a liquid, and you can actually then transfer that to another part and just withdraw it completely. The unused hydrogen and nitrogen that comes out from this reactor, because it doesn't actually the reactor doesn't actually allow the equilibrium to be fully established. It just allows a 15% yield of ammonia. That's good enough, and you actually also recycle the hydrogen and nitrogen that is unused, and you allow it to pump all the way through under pressure using this compressor and allow it to then react again. So the equilibrium mixture is a balance between nitrogen, hydrogen, and ammonia coming within the reactor itself. If you cool the mixture down, the ammonia condenses first, so you can just run it off as a liquid, and then you just warm the remaining nitrogen and hydrogen again after it comes out of the condenser, and more ammonia then forms, and you just keep doing that continuously. The other thing that you can do is you can use a catalyst. So it's really important for me to emphasize this point. The catalyst does not shift the position of the equilibrium to the left or to the right. Doesn't shift it at all whatsoever. What a catalyst does is it effectively weakens the bonds of whatever it is that can react to form your product. So remember that we have two reactions taking place at the same time. We have a forwards reaction and we also have a reverse reaction. So a catalyst speeds up both the forwards and the reverse reactions equally. The reaction reaches equilibrium faster, which can save us time, and it can also save us money because it generally costs money to keep the reactor warm. But the amount of ammonia does not change. Okay, the amount of ammonia doesn't change. You just get to that yield in a much quicker time. So using a catalyst does not shift the position of the equilibrium left or right. It doesn't make you any more ammonia. It just gets you to the amount that you can make in a quicker time. So the optimum conditions for the yield of ammonia are as follows. Use high pressure whatever you can achieve to keep the process profitable, because high pressure is something that is generally dangerous. So you do need to have thicker pipes, more safety around the condenser, a more powerful compressor, and so on. So you do need to have, it will cost to maintain it, it will cost to actually build it as well. Those costs actually have to be made back when you are, as an industry, making ammonia. So using high pressure is a good thing, but you can't just go for the highest pressure. But you do have to raise the pressure significantly. If you remove the ammonia, that also drives the equilibrium over to the right-hand side and makes your forward reaction rate higher than before. That helps you improve the yield. Use a moderate temperature, not too high, because the forward reaction for this particular reaction is exothermic, and that means the reverse reaction is endothermic, and you won't want to encourage the reverse reaction happening, else all of that hard work that you put in to make the ammonia is lost completely. The ammonia just breaks down and forms hydrogen and nitrogen, and no product is made. And you use a catalyst to get a decent rate, because what you want to do is you want to make your ammonia in as short a time frame as necessary. So a couple of questions to help you promote your thinking. You can pause the video and have a go at this one. The reaction between nitrogen and hydrogen is reversible. This causes a problem for the ammonia factory. Why is that? So pause the video. Okay, so my model answer for this is because it's not possible to convert all of the nitrogen and hydrogen. You'll never get a 100% yield. So special steps must be taken to increase the yield as much as possible. Here's your next question. So pause after I've read it. In manufacturing ammonia, explain why high pressure is used and ammonia is removed. So pause the video. Okay, so firstly, you use high pressure because by reducing the number of molecules present, more ammonia forms from the new molecules of nitrogen and hydrogen. And secondly, you remove the ammonia because more ammonia forms to replace what is removed from the equilibrium mixture. It increases the yield and shifts the equilibrium over to the right-hand side. Okay, we'll finish it there. That's a quick sneak peek of what the next video will be about. The next video will be about the contact process and the formation of sulfuric acid. But hopefully you are now able to uh, understand that a reversible reaction in a closed system is at equilibrium when the rate of forward reaction is equal to the rate of reverse reaction and the concentrations of reactants and products are no longer changing. And you can predict and explain for reversible reactions how the position of equilibrium is affected by changes the temperature. So if you raise the temperature and it's exothermic, you're actually going to have more products turn back to reactants. So don't do that because the reverse reaction is endothermic. Change in pressure. So pressure matters when you have different gas volumes. So if you are generally starting with more gas volumes and your target, your products are taking up less gas volumes, raising the pressure is actually a good thing. Changing concentration. So if you increase the concentration of the reactants, generally you will then drive the equilibrium over. So you'll shift the equilibrium over to the right-hand side on the product side. And using a catalyst doesn't affect the yield, but it gets you to gets you to the equilibrium faster and could be more cost effective. And that's it. Thank you for watching. And the next video that I'll be doing will be on the contact process.